Hello and welcome to the session. In today's session, I'll be discussing with you about floating point representation. Now, what do we mean by floating point representation? Well, most of the time you had been confined. You must have seen that we are dealing with integer numbers even in computers. However, sometimes you encounter real numbers in computers also. So if a calculation is to be performed with the help of real numbers, can it be performed with the help of integral representation or sine 2's complement notation, which you already know about computers? Well, it won't be possible. Why? Because it is going to truncate all the points after the decimal. And once all those points are truncated after decimal, obviously the calculation which is going to be performed is going to result into lots of truncation errors. I mean, and those truncation errors will definitely be of very high nature. In addition to that, what is the highest integer number which you can represent in computers? Suppose you are representing with 16-bit. Okay, it will be 3266767, that is positive, and on a similar, roughly one more in the negative side, because you are representing the numbers using sine 2's complement notation. Whereas when we are dealing with real numbers, we are representing those numbers in the power of 10 to the power 5, 10 to the power 6, and those powers are to be multiplied with another number having the similar kind of powers. So how to represent? So the question is how to represent these numbers into the real computer systems. Well, for that, now please note the idea, the floating point. We'll talk about the term floating point, why it is called floating point. That is also very, very important, but I'll talk about that a little bit later. But first I would like to talk about what this particular representation is. Well, floating point representation consists of two parts, right? The first part, it is called the signed fixed point number, right? So the first part is which we call mantissa, and sometime we will be referring to significand. That is the term we will be using, significand, right? And the second part is the binary point position, which is represented with the help of an exponent. So these are the two major parts. Slightly confusing at this point of time, but we'll take up the example of this particular thing a little bit later. The second point mentioned over here is that the mantissa can be an integer or a fraction. Now this is very, very important. Okay, we'll talk about this once again. And final point is, please note that the position of binary point is assumed and it is not a physical point. Now three basic points we have mentioned over here. The first point clearly indicates that we are referring to any number in the form of mantissa as well as exponent kind of a thing. And then we are saying that the mantissa can be either integer or fraction. Now which one we would like to choose and why? Well, to go on to that, let's try to first look into a decimal number which we are representing with the help of a floating point, and that's where the concept of floating point is going to be clear to us. So let's try to look into example 1 now, and the example basically this is showing a number plus 12.34 in a typical floating point representation. So these two are the ones. First one is the mantissa, which is considered to be fraction in this particular case, followed by the exponent. Now the number is plus 12.34, and sign also is to be represented, and since sign cannot be represented by any other thing, we have to represent the sign with the help of a number only. So we chose 0 to represent the positive sign and 1 to represent the negative sign, and so is the case with the exponent. So look into the number representation over here. What we have done here, sign is 0, that conforms to the plus. Then 12.34 gets converted into 0.1234. Now this is a case of fraction. Mantissa is a fraction, complete fraction. So that's why it is starting with 0.1234. Now in the process, since we got 10 to the power 2 available to us, we divided the number by 100. That's why we got this particular fraction. So that 100 is being represented in the form of an exponent, which basically is plus 2, right? So because 10 to the power 2 is 100. So then if you multiply 100 with 0.1234, you will get back your original number. So that's how you get your representation, right? Which is 0.1234 multiplied by 10 to the power plus 2. So this is the representation. This is one of the representations which you can do as far as floating point numbers are concerned. The second floating point representation which is possible, once again sign remains the same, but mantissa in this particular cases changes to integer. Now if this is an integer mantissa, right, 1, 2, 3, 4, then the exponent in this particular case is going to be negative, right? So that's how this particular 1 is appearing over here. And since you have moved the point by 2, 1 and 2, so this is going to be negative 2, and what the number which you are getting is I think this is 0. It should not be 0 point. It should be, just omit the 0 point. It should be 1, 2, 3, 4 into 10 to the power minus 2. That's how it is going to result into 12.34. So it has to be 1234 into 10 to the power minus 2. So these are the two basic representations for the number as far as the floating point is concerned. Now notice one particular thing in both the situations. The point we said is here or there. That was our assumption. In fact, while representing the number, we stated that particular fact, that we are assuming whatever is going to be represented. There is no representation for point as far as floating point number is representation. The point position is assumed, and most of the cases whenever you are dealing with floating point representation in binary system, we will be using a fraction kind of mantissa rather than integer kind of mantissa, because integer kind of mantissa lends yourself into different kinds of problems, because it becomes an integral, and handling integral becomes a different ball game once again. Whereas fractional mantissa is one of the on that particular basis we will be discussing something more about like precision and those kinds of things which are the need as far as the floating point number representation is concerned. Now why we call it floating point? Could you notice the point position is dependent on the power, exponent power. So if 12.34, okay, that's 10 to the power 0 multiplied by 10 to the power 0. The same 12.34 can be 1.234 into 10 to the power 1. Same 12.34 can be 0.1234 into 10 to the power 2, and same 12.34 can be 12,034 into 10 to the power minus 2. So now you look into all these aspects. The position of the point is also dependent on the exponent power. So that's why this is a floating point. However, since we are representing that particular number in a computer system, we have to assume a position of the point, and that's where we will be assuming just before that is 0.1234 is probably one of the representation which we might be choosing as far as computer system is concerned. Obviously, we won't be representing that particular number with the help of decimal number system. We will be representing with the help of binary number system. So let's move from decimal number. Let's move on to a binary number system, like how we would like to represent number. We'll start with the decimal number, and we would like to represent it with the help of a binary floating point representation. But first we will represent it with a very simple representation. So let's look into an example 2 now. What do we have now? Decimal number is plus 10.125. And if you want to convert it into binary equivalent, you will get plus 1010.001. You can do this particular conversion by yourself. So we are concentrating on this particular number, 1010.001. Now, floating point numbers are often represented in normalized form. Normalized form means fractional mantissa does not contain 0 as the most significant digit of the number is considered to be normalized form. Now, this is something which we need to understand here, that what is the normalized form. So we will be moving the point to the extent we get the last one in this particular direction. Luckily for us, the first the most significant bit in this particular case happens to be 1. So we will be moving this point to 1, 2, 3 and 4 position down, and it will appear over here. So this is the way we will be representing the whole thing, and point is assumed to be at this particular position before the fractional mantissa. So what you will be representing the number to be 1010, that is this, no point after that, 001, because point we have already moved before this particular one here. The sign happens to be 0. Since we moved the point by 1, 2, 3 and 4, right? So this is what the exponent is turning out to be. This you can say this is 2 to the power 4, right? So the number now we have is the sign bit for the mantissa happens to be 0, as the that particular digit was 0. And the fractional mantissa in this particular case is 10100001, and exponent happens to be the 2 to the power 4, which is represented as 0100. Now this is it a binary? Can I represent this particular number in the similar way into the computer system, or do we need certain more standards? Probably we won't be. I mean, the point is fine that we are able to represent the number in the form of normalized mantissa, but normalized mantissa, how big should be the mantissa? How big should be the exponent? Right? Now these are the questions which we need to address, because we have to design a system in which we are able to represent the numbers. So was the case for as far as integers were concerned. We chose, let's say, 16-bit as far as integers were concerned, and the first bit then was chosen as the sign bit, and the magnitude then was taken as the for the positive numbers, and 2's numbers and the negative numbers were represented with the help of sign 2's complement notation. Now we chose a typical format. We chose a typical length of the field. Okay, so is the case as far as floating point numbers are concerned. So we have to represent two basic things over here: the mantissa and the exponent, and both of those, mantissa as well as exponent, may have the sign. So whose sign will be, do we need to represent sign of both, or can we get away by representing sign of one and do some other jugglery with the other part and do not represent the sign? Because I mean, it might be confusing, like one sign for mantissa and one sign for maybe exponent or that kind of a thing. So can we do some other things in that particular case? After all, sign is for the mantissa most of the time. So exponent we might not represent with the help of a sign, but something else. So a binary system, in a binary system, let's try to represent the number which we have studied, like we have got, with the help of a system. And we first represent, I present to you first the representation, like 32-bit representation, which we will be using, and then we convert that particular number into this particular form. Now this is a hypothetical one, remember that. It's a hypothetical one, and after that even one more standard exists, which is followed in most of the computer. This hypothetical representation we have chosen just to explain to you how this particular system can be represented. Now if I look into this particular representation, there will be one bit for the sign. Right? So we have one sign bit, then we have 8 bits for the exponent. Okay? So first one bit is the sign bit, followed by 8 bit for the exponent, and thereafter 23 bit for significand or mantissa. Okay? And there are several conditions attached to this particular hypothetical representation. Now the first condition is that the leftmost bit is the sign bit of the significand. So that's what this sign bit is going to be, the leftmost bit, right? It will be followed by the exponent bits, 8 bits, and that will be followed by 23 mantissa or significand bits. Mantissa or significand should be in normalized form, right? So now this is what our expectations are, and this is where we will be bringing in another fact, but for the time being what we are assuming that mantissa or significand, this should be in normalized form, right? So we will be doing it, and definitely this significand actually is a fraction. That's what we are assuming, although it's not been stated, but what we are assuming here that the significand is a fraction. Okay. The base of the number, we are representing this, we have assumed this particular number representation since we are using the binary, so we will be using the base as 2, right? We will be doing with exponent. Now mind this particular thing, this sign bit is for the significand. So what happened to the exponent? It doesn't have any sign bit attached to it, just 8 bits are there, right? So what do? We do a value of 128. Okay, now we know that the exponent is 8 bits. So in 8 bits we can represent number, unsigned number. If we don't assume the first bit to be the signed bit, then our number representation is in the range of 0 to 255, right? 0 to 255. So whatever is your exponent, what we will be doing, we'll be adding 120 to 8 to it, right? So suppose your exponent in the example which we were using, so exponent was 4. So in our case it should become 132 in the representation only, right? So we will be adding 128 to the exponent. Now the question asked is why, right? Now if you take this particular example, we have added 128 to the number, right? So if I have an exponent of minus 128, what will it become? Minus 128 plus 128, 0, right? If I have an exponent plus 127, what that particular exponent will become? Plus 127, right, plus 128, this becomes 255. So effectively in the representation, if in your representation you have the exponent value as 0, all bits 0, what does it mean? It is representing an exponent minus 128, right? And if the exponent is 255, then the actual exponent of the number which you are representing into this particular representation is plus 127 only. So what you have done effectively, by having a bias of 128, you have shifted the range of 0 to 255, that is what is representable in the exponent component, from, and you are shifting the range back to minus 128 to plus 127 of the actual numbers. So you have done a very smart thing. You have done very smart thing by adding a bias as far as exponent is concerned, right? Now this is one of the most important consideration whenever you are designing a floating point number, because too many sign checking in one particular number is, the more difficult the circuit becomes. Now in this particular case, sign checking is not required. The number range is very well defined. The exponent range I'm talking about. The exponent range is very well defined, and exponent is just a binary number, right? So that is the way, by representing, by doing a smart thing, I'm able to do a smarter thing, that is, I just have one bit representing the sign. And that's what computing science is all about, putting in small smart things together and bringing up a very useful device for your use, although that particular device, you know, can only perform calculations. But your logic, our logic, is making smarter and smarter every time by putting in many programs and many more things. Right. So let's continue with our discussion what we were doing about this hypothetical machine. So let's know some more facts about that hypothetical machine. So a normal exponent of 8 bits normally can represent exponent values as 0 to 255. This is precisely what I was saying. However, as we are adding 128 for getting the biased exponent from the actual exponent values represented in the range will be minus 128 to 127. This is precisely what I explained to you just now. Then, as we are representing normalized mantissa, right, which basically implies the leftmost bit cannot be 0, right? Therefore, it has to be 1, right? Now, mind it, in the case of the only problem for this particular argument is when we are representing a 0, right? Then you are going to face problem as far as representing the number is concerned, because 0 cannot be normalized. But this particular problem exists over here, and that's why I'll say there is another format which exists, another standard which exists, which is followed now in all the computer system for implementation of floating point number. But there is a problem with this particular representation. That does not stop us from understanding this particular number representation, right? So we go on to our assumption, and we say the leftmost bit cannot be 0, therefore it has to be 1, right? That's as simple as that in a binary system. So do not store this first bit, and this bit can be assumed implicitly, right? This first bit you can assume implicitly to be 1. It's going to be 1 all the time. What does it mean? You can assume not only the position of the point, but you can assume 0.1 followed by how many bits you had for the significant? 23 bits. So the overall significant in this particular case becomes 0.1 followed by the 23 bits which you are representing. So the total length of significant is not 23 bits, it's 24 bits now, right? Despite all that particular thing. So what we are saying, therefore a 23-bit mantissa can represent a 23 plus 1. This 1 is for the implicitly assumed bit. Why? Because we are following a normalized representation. So the overall length of that particular number becomes 24-bit, right? So we are representing in 23 bits, we are representing 24-bit mantissa. Isn't it smart? That's very nice. I mean, that's what I was telling you. You keep on adding very simple, smart things and make a very smart computer for yourself. So what we have now, we have 32 bits. Out of that 32 bits, 8 bits are representing the exponent, 1 bit is representing the sign, and those 23 bits actually are representing 24-bit mantissa, right? Okay, so this is what I have to say about the representation. But where was our example? We were discussing some example. So let's bring in the example now, and let's discuss about the example in the parlance or in the context of this particular representation. So once again, the binary number which we were discussing was plus 1010.001, and we found out that the sign bit for this, you can look into these sign bits. There are lots of colors which I have used in this particular slide. So just have a look at this slide. So what can you see now? Sign bit we have represented, just given a color green. It does not mean it is going to be of that color, but then just a color. Now fractional mantissa. What was our fractional mantissa? 1010001. That's what it is. 1010001, right? And the first bit, what we said in our representation is implicit 1. So this is a normalized bit. So we are okay. So this is going to be an implicit 1. So we need not represent this, right? And the exponent which we have got is 4. That is 0100. Right. Now, in the proposed floating point representation, how we are going to represent this 1010.001? Let's look into this. Sign bit remains unchanged, so we get sign bit. Okay. Now, after the sign bit, what do we have? We have the exponent. Where is the exponent? Okay. To calculate the exponent, what we are doing? Add bias. And bias was what? How much? That was 128, sorry. So this is 10100000 in 8 bits. 128 is going to be this, right? Add 100, which was 4, this exponent over here. What do you get? 100000100. So this is 128 plus 4, 132, right? And this exponent is coming over here. So look into it, 10000100. This is 132 in total, which is the exponent after adding the bias. So we have represented the exponent and its sign without any problem because had it been 1, then we would have subtracted that from this particular thing, right? Maybe we could have represented this in the form of sin 2's complement notation and just added into 128 or whatever. But this is the way we can represent this particular number. All right. Okay. Please check. Please check. You can check this particular thing. There might be something over here. Anyway, this is something which you can refer to as far as this particular thing is concerned. Then comes, look into this particular one with a different color. Actually, this one stands for this particular white one, the fractional mantissa portion. Actually, this shows that it is not to be represented. Okay, because after that the mantissa is starting, and this one is not represented. That's why it has been shown with a different color altogether. So this actually does not exist, but it is an implicit one. Why it is? Because this is the one which is being represented, and it is implicitly assumed in the mantissa. And thereafter you have 010, which is coming over there, followed by 001, which is coming over there, 0. And thereafter all zeros. These are required to complete the mantissa of 23 bits. So you can see 4, 8, 12, 16 plus 4 of these, 20 plus 3 of these, 23. This is not represented, 23 bits mantissa, 8 bit of exponent, 23 plus 8 becomes 31, and 1 bit of sign. Total is the 32-bit representation of the number plus 1010.001 into this particular form. Okay, when you want to reconvert it into your form, right? So what you will do? You will extract this, okay, convert it into equivalent decimal, right? And then as per the point, you will be subtracting 128, so you will be getting 4, so you will be getting 1010.001 back your number, and then you can convert it back to the digital format, equivalent digital format. So you just have to follow all the reverse operations in this particular case. Isn't it easy? It's really easy, but this is one of the most misunderstood portion as far as binary numbers are concerned. So floating point numbers should be dealt with very, very clearly. If you understand the logic which I have explained to you right now, once again, sign bit comes as it is, exponent is added with the bias, and that added component is put over here. Then this one is not being represented. Why? Because it is being assumed implicitly, so there is absolutely no reason why we represent it. Remaining bits find their place in the initial one, and the remaining zeros are coming, padding, you do the padding, so that the mantissa, overall mantissa size of overall mantissa becomes 23 bits. So this is the way of converting a simple number into a floating point number. But as I told you, our representation is not a very good one. Still we will do, we have chosen this representation because we want to do some more things. We want to show some more things with this particular representation to you. And that more thing is, like, first thing I would like to talk about is the number range, which the representation which we have chosen can represent. To do so, we have done some work. So let's look into the smallest mantissa value which is possible in this particular number representation which we have. So the smallest mantissa will be the implicit first one. We are not talking about the sign in this particular case. So the implicit first 1 bit, right? So the first 1 bit is implicit, and it is followed by 23 zeros. So what do we get? 0.1 followed by all 23 zeros, which happens to be 1 into 2 to the power minus 1, which happens to be 0.5. Okay, so this is one major problem which we are facing in this particular representation. The maximum value of the mantissa, right? So 0.5, and if I represent the maximum negative exponent with it, so 0.5 divided by 2 to the power 128, that's going to be the approximation for 0. 0 cannot be represented by this particular range. The maximum value of the mantissa for our case will be the implicit first bit followed by 23 ones. So maximum value of mantissa once again is going to be 24 ones, right? First, this is implicit, this portion, okay, till first point, 0.1, and thereafter 23 ones. And if I add, just to, simplify this particular calculation, like rather than calculating all ones into decimal equivalent, it may be a good idea if I simply add just all zeros, 23 zeros followed by a 1 into it. So what is that? That is 2 to the power minus 24. Right, that is representing 2 to the power minus 24. If I just add 2 to the power minus 24 to it, so what will I get? A 1, because everything will get added to 1. So I get 1. So this particular mantissa, overall mantissa, is actually 1 minus 2 to the power minus 24. So this is the value of the mantissa. So in fact, what you are saying, the minimum mantissa which is possible in this particular representation is 0.5, and the maximum mantissa value in this particular case is 1 minus 2 to the power minus 24. Now continuing with this particular number range, therefore the smallest negative number, what we will be able to do, maximum mantissa and maximum exponent. So this is the smallest negative number. The maximum mantissa was 1 minus 2 to the power minus 24 with the negative sign into 2 to the power 127. So this is the smallest negative number, right? Onto the lowest side, whatever we can go. Largest negative number which we can represent, the minimum mantissa, which happens to be 0.5, and minimum exponent, which is going to be 2 to the power minus 128. So minus 0.5 divided by 2 to the power 128, and if you will find out a very, very low figure, this is going to be very close to 0, but not exactly 0, but very, very close to 0, right? Smallest positive number is going to be once again the 0.5 into 2 to the power minus 128. Once again very, very close to 0, but not 0. So 0 is one number which is troubling us a lot in this particular case, and largest positive number is going to be 1 minus 2 to the power minus 24 into 2 to the power 127, which is going to be very, very large number in this particular case. So we are able to represent a whole number range in that 32-bit representation. 0 definitely is doing some kind of a trouble to us. And if we go from one machine and have a different representation in a different machine, we are definitely going to face lots of problems into our machine situation. So one particular fact about the binary or the floating point number system is the the number range which it can represent, the 32-bit number. The second thing which is very important as far as floating point representation is concerned, it's called the precision. So let's look into the precision. Now what we are saying, basic trade-off is between the range of the numbers and accuracy, and accuracy is basically called the precision of the numbers. What do we mean by that? The accuracy of number will be higher with bigger mantissa. So the bigger is mantissa, higher is the accuracy. Now let's explain it with the help of an example. That is, for example, with 1 bit binary mantissa, you can represent only 0.10, where 0.1 is the assumed one, and 0.11. So only these two numbers we can represent in the normalized form. Whereas with 2 bits, the values such as 0.100 to 0.110 can be represented as completed binary or as complete numbers. So you keep on adding more bits and you will be able to represent numbers better. I mean, this is as simple as that. Even if you are performing a decimal arithmetic and you just truncate all your results till 2 digits, ultimately you will encounter the truncation errors or the round off errors in that particular case. And so is the case with the binary. The bigger is the size of the mantissa, it's going to be more accurate, right? So we want bigger mantissa, but we don't want to compromise the range of the number also, right? So less precision will create a truncation or round off error. This is what I said. The higher the number of bits in mantissa, better will be the precision. So this is the main focus of us. So what do we do? Right? So we jump on to a very important representation. In fact, IEEE standards have been designed for binary number system. And what is the reason? And there are 2 basic standards over there. 2 basic standards. This is for single precision number and double precision number. Now, why we needed IEEE standards? We needed these standards because we don't want to deviate from one machine to second machine, where if suppose 0 is not being represented, then what is going to be the problem in a particular situation. So let's look into the single precision number, IEEE standard 7.5, and how it is being represented. Exponent, significand, and value, etc. So if exponent is 255, it's 8-bit exponent. Once again, remember that exponent is 8-bit. It's very close to what we represented. 8-bit exponent, the first sign bit, and 23-bit mantissa. The same thing it is there, significand, right? So if the exponent is 255 and significand is not equals to 0, then we say it does not represent a number, right? Similarly, if the exponent is 255, right, the highest number, but the significand is 0, then we say it is minus or plus infinite depending on the sign bit. So this is the definition of infinite, and whenever we are dealing with numbers in computers, infinite has to be defined, which basically represent that we have landed ourselves into trouble, because beyond this the numbers cannot be represented in computer. So infinite has to be defined as far as if you are dealing with binary floating point or fixed point number. Even in fixed point number, when you were adding and the number it was going beyond that, then there was a condition of overflow, right? So is the case as far as IEEE standards are concerned. Thereafter, if the range is between E is between greater than 0 and less than 255, which is the representable range, then please note there is a major difference here, plus minus 1.n, and what we were assuming 0.1 and followed by n. That's why you will find E minus 127. Our case was E minus 128 in our case. So we move it by 1 and reduce this by 1. Why? Because it really is a slight difference as far as representation is concerned. Not major difference, but then you have to understand that the representation now is 1 point. So implicit is 1 point and not 0 point, what was in our representation. So implicit thing is 1 point, and then n is whatever is that is n is the significant. So significant comes as it is, because that implicit 1 which we said 0.1 followed by n in our case. In this particular case it is 1.n, and plus minus follows as it is, and exponent you will see it is bias of only 127 in this particular case. So you will be adding, actually whatever bias is there, you will be adding only 127 to it, and number will be represented with the help of 1.n and not any other thing, right? So n still remains the same. Notice that, right? N is not going to change. It is the meaning which is going to change slightly, right? So for example, n is equal to 101 for rest 20 zeros, and E is 207. Now this particular thing will be is equivalent to 1.101 and 2 to the power 80. So this is what is an example which is represented over here. So that's what we are saying. 1.101, which is 101 was n, so it comes directly. 1 point we have assumed implicitly, so it comes over here directly, and exponent, the bias of 127 is reduced from the exponent, and what you get is plus 1.101 into 2 to the power 80. So this is a typical example of one of the number which has been represented. Sometimes you are asked to do the reverse operation. So suppose you were asked, you have been given 0.1101 into 2 to the power 81. So first you will convert it into 1.101 into 2 to the power 80, and then what will you do? Okay, so 1.1 is assumed 101, that becomes your the significant, follow it by 23 or 20 zeros, make it 23 bit, and then this in the Mantissa you will be adding 127, so 80 plus 127 you will be getting 207. So forward as well as backward, both the way you should be able to understand it. Now finally over here, what you can refer to, when the exponent is 0, then the number 0 is being represented. Okay, so this is 0.n. In this particular case it is same as what we were doing, but there is no 1 in this particular case. So it is 0.n 2 to the power minus 126. So you can see this particular thing is taking care of that there can be a 0 in this particular case, and if everything is 0, then depending on the sign bit it is 00. There is one more double precision format which is exactly on the same line. However, in this particular case the size of exponent becomes 11 bits, and the significant in this particular case will become, because this is a 64-bit representation, so 11 and 1, 12-bit goes for that, so we are left with 52-bit significant, right? So that 52-bit significant are possible, which is called double precision, and you can see that this double precision number is almost, in fact, entirely onto the similar line as the single precision number, except that the precision or the number range as well as precision is going to be higher in this particular case. And why do we need that? Obviously, for better calculation performance, you are not going to have truncation or rounding off errors as far as the double precision number. So most of the calculations are done in double precisions and not into the single precision, but the result is then truncated to single precision, and you can represent the number in a single precision number. So what we have studied in this particular session is I have explained to you the floating point representation format, which primarily is utilized in computer. We started with a very simple representation, a hypothetical representation, and that was important so that we can move on to understand the IEEE 754 format for single as well as double precision. So for the time being, bye from me, and I'll be seeing you next month with another lecture. Thank you so much.